Okay, good morning. And hello, everyone. Can you hear me? Is this good? Yeah, okay. Hold on, just bear with me for a second. Je vous remercie de votre invitation à présenter à cette conférence. Okay? Thank you. Thank you. That's everything I'm going to say in French. I'm sorry for my bad French. And if you don't mind, I'm going to just dive right into the technical meat. One of the things I want to say is that I enjoy interactive conversations when I give talks. So feel free to ask a question. You don't even have to raise your hand. Just say it, and I'll stop and explain. Especially, it's important that I'm going to, it's a big audience here, and I'm not familiar with everyone's sort of expertise. And if there is something that doesn't make any sense, it's my job to help you understand, so you should stop me and ask questions. I think it's best to actually make sure that whatever it is that I talk about, it's understandable and makes sense, rather than me making sure I get to the end of the talk. It's better to just make sure everybody's on the same page, okay? Okay, so this body is about a body of work that spans about 5-6 years, most of which was done on Microsoft research, but in collaboration with many researchers, many engineers, and many students. Now, I want to tell you a little bit about Microsoft Research. Microsoft Research is the research lab of Microsoft, and we have a great job. Our mandate is to push the state of the art in computer science. So what that means is basically doing research and publishing papers and so forth. By the way, I was told that I can drink chartreuse during my talk. I don't think I've ever actually drank during a talk, so I'm going to take this opportunity to do that. That's very good. Okay, so that's Microsoft Research. I build systems, so I would like to see the results of my research actually being pushed into actual real products at Microsoft. So this talk covers 2 projects. One that shipped and one that did not ship. One that's researchy and one that's not. Any questions? You need to ask questions. I'm not going to continue until you ask a question. I'm not kidding.
You want to sit on?
No, it's good. I still have some. Questions? Do you have questions about Microsoft? Come on, you have to have a question about Microsoft. Microsoft Research. How many of you know about Microsoft Research? There is a research lab also in Europe, in Cambridge. Okay, so let me just move on. So I'm going to talk about 2 projects. So I want to motivate a little bit this kind of work. Clearly, we're looking at smartphones because that's what the sort of the device of the era is. The smartphones' growth clearly surpassed those of PCs. And I'm going to use the term PC here not to just mean a Windows machine necessarily, but just sort of the traditional desktop and server machine that we've been using, whether it's Windows, whether it's Mac or Linux, okay? And clearly on these smartphones, we have a lot of sensitive data where we're actually afraid to lose or get it stolen, whether that's email or contacts, or photos, or health information, or financial information. This data has value. One of the things I want to mention is that a lot of people think about this data having value on smartphones, and that's true, and I'm going to talk about that. But there is also a different type of sensitive data that actually our smartphones gather. And these are data that comes from the sensors. And there is a new class of mobile applications out there that rely on this data coming from the sensors, gathered by the sensors, to be accurate, to make sure it's not being counterfeited or compromised or fabricated. And here I'm listing 3 applications, or 3 classes of applications. At the top, I have this check deposit application. In the US, so our banking systems is sort of very backwards. We continue to use checks to conduct financial transactions. Before smartphones, the way this would work is you'd receive a check and you'd run to the bank and cash the check. Now, with the smartphones, you take a picture of the check and send it to the bank, and then the money comes to your account. So clearly, the bank has a huge incentive to make sure that these checks have not been counterfeited or photoshopped in some way. On the right, I have mobile health applications. There are these applications that use sensors, whether the smartphone or sensors on your body, that collect data. And again, this data has to be there is a huge incentives for users, doctors, and even insurance companies to make sure that the integrity of this data is protected. And at the bottom here, I have what's called crowdsourcing applications. Crowdsourcing applications are this class of applications or a cloud service that tries to sort of build a map of the world by extracting information from everybody's smartphones. In this photo here, I have a concert application, but a better application, I think, is one that I'm sure many of you use when you drive around, like Waze, for example, where you use it to actually navigate, but at the same time, your Waze application sends data to the clouds so that Waze can actually better serve real-time traffic information. And it's important for Waze to make sure that this data is not being fabricated, okay? So what's the point of all this? Well, data gathered and stored by smartphones has high value. And the way I think about it, whenever data has high value, it attracts sort of attacks. And there are two classes of, or bad guys. There are two classes of attacks. There are third parties, and this is a traditional attack where you have malware that tries to steal your data from the phone. But also first parties that want to fabricate, like users or applications that want to sort of alter the data or fabricate it in some way. So data is under attack, not just from malware, but also from applications and users. And it gets worse. So here's sort of my other observation, which is that mobile devices arguably are much more easily lost or stolen than PCs ever were. It's really easy to lose this, right? And the observation here is that data loss can also be due to device loss. And once an attacker has access to the device, there are all sorts of attacks you can actually mount on the device, like memory attacks, trying to read what's in the memory of this device. By the way, right now, on the memory of a smartphone, on my smartphone, there are all sorts of sensitive data living in RAM. And it's really not that complicated to read the RAM directly. And I'm going to talk about attacks to your phone's RAM. Oh, one thing I want to mention is that these physical attacks, these attacks where the attacker has access to the machine, to the computer, we had these attacks in the past with PCs. People worked on them, but they were at the sort of at the fringe of the research community because it was, relatively hard on average. Not hard. I want to say hard, but people were not losing their desktops that much. My desktop sits at home. I don't think I ever lost a desktop. Whereas I'm sure there are many of you in this room who have lost smartphones or tablets. Okay, so this talk presents two approaches to this sort of motivation, to this research agenda. So what we try to do at Microsoft Research is to build software abstraction for mobile devices. We build a software-only implementation of a TPM chip. Now, I need to stop and ask you, how many of you know what the TPM is? Oh, wow, okay, good, excellent, okay. So TPM stands for Trusted Platform Module. You can think of it as being a secure coprocessor. It is a secure coprocessor. Many laptops, to a first approximation, all laptops that enterprises buy today have TPM chips in them. And even many of the consumer laptops you buy to them have TPM chips in them. Many of the laptops here have TPM chips. So we build a software-only implementation of that, and I'm going to talk to you about it. We also build trusted sensors. Sensors whose readings we can have higher assurance that nobody has tampered with, okay? And we build software abstractions for them. And we also build a cloud TPM. A cloud TPM is this idea. TPMs are very good at protecting and giving you security guarantees, what's called per platform. What platform typically means is a machine. They can actually offer you sort of storing the credentials, storing keys, storing passwords, and having high protections on a single laptop or on a single device. The cloud TPM idea was to sort of give the same protection seamlessly across all devices that the mobile user owns. The observation here being is that many of us have multiple smartphones or a smartphone and a tablet, and we want to, whatever we secure on one platform to be seamlessly available on another one. And today doing that with TPMs alone is very hard. The second thing we do is we're trying to build new systems that leverage trusted hardware. One example of a trusted hardware is the TPM chip. That's a trusted hardware, but I'm going to talk about other examples in this talk. Sentry is a data that tries to protect data, Sentry is a system that tries to protect data against memory attacks. And TLR stands for Trusted Language Runtime. And the idea is to offer trusted computing primitives at a very high level in .NET. And we build this for .NET because we come from Microsoft. All these ideas can be done on JVMs or Java. There is nothing special that we use from .NET here. So the idea here is that the willy-nilly mobile app developer can easily take a piece of the mobile application and leverage trusted hardware. And for those of you leverage, for example, for smartphones, is ARM Trust Zone is the trusted hardware available for us on ARM to build portions of the applications that way. Okay, how many of you are familiar with Trust Zone or have heard of Trust Zone? Okay, less than TPMs. Okay, and I'll talk about Trust Zone, so no worries. I didn't get any questions other than somebody offered me to get more chartreuse. Yes?
Why do you are only Apple product on your slide?
I'm sorry?
Why do you have only Apple product on your first slide and not Microsoft?
Oh, okay. I actually stole that. You mean the picture of the iPhone? Yeah. It's getting even worse, actually. I have an iPhone myself. So actually, I have to be careful what I say here, but Windows Phone market share in the last earnings report fell by 72%. Okay, so I'm not speaking on behalf of the company here in any way, but sort of the Windows Phone story is not very good at this point. On the other hand, we use Surfaces, and what you're going to see next actually appeared in Surfaces. And I'm a big fan of Microsoft Surface. I actually use one all the time. I have one in my hotel room. I didn't bring it here. Okay. So in this talk today, I'm going to talk about the first and the project in each of them. And I want to talk a little bit about the acknowledgement. So this work was done with many, many other collaborators, and I've been very lucky to work with a whole bunch of smarter people than I am. In general, my rule of thumb is to try to always work with smarter people. It's actually not very hard for me. Okay, so Alec Woman and Himanshu Raj at MSR and many other researchers, and I'm going to mention them on the next slide. We have summer students at Microsoft Research, both in Cambridge and in Redmond and in other labs. We also have labs in Asia as well. And Patrick, Hay, or Lonnie, and Chen and Nuno actually were wonderful students I work with. And I also have quite a few collaborators. I was a professor at the University of Toronto before joining Microsoft, so I have strong ties to Toronto. And I work with that group there. And also I have strong ties to the Max Planck Institute in Saarbrücken, Germany. Okay. FTPM. FTPM is so from now on, my talk is in two portions. And it's very clear which portion we are in. So there are basically two talks that are sort of combined into one presentation here. And this is the first one. FTPM is a software-only implementation of a TPM chip. The F in FTPM stands for firmware. And the reason why this is called a firmware TPM is because the software-only implementation runs in the firmware of a device. The FTPM was a large project, and there are many researchers and engineers at Microsoft, and I'm not going to name all of the people here. Those of you who are deeply familiar with TPMs, or maybe some of you are parts of the TCG or members of the TCG, I'm not going to talk about these things. Maybe you can recognize some of the names here. We also work with the companies that are producing the hardware where Microsoft Windows operating system runs on. So we work with three what's called SoC or system-on-chip vendors. And these are NVIDIA, Qualcomm, and do you care to guess who the third SoC vendor is, system-on-chip? So Qualcomm, right? I mean, I'm sure many of you have Samsung devices. Those Samsung devices run Qualcomm chips inside of, or they run ARM chips made by Qualcomm inside of them. NVIDIA is another very popular platform. There are many devices out there that use NVIDIA ARM SoCs, system on chips out there. Who do you think it was the third big company whom you have heard of that Microsoft worked with as a system on chip vendor?
Apple, I would say.
No, not Apple. No. No, Apple likes to put, Apple is also an SoC, but they don't sell their chips. They just put them in their iPhones and that's it. They don't, yeah. Apple has their own thing, right? So they build everything from the ground up. Who's the third SoC vendor you think Microsoft or this thing we worked with? Very good. And the reason why I say very good is because Intel doesn't, okay, I shouldn't say that because that's not true. But the SoC we used for Intel was not an ARM SoC, it was an Intel SoC. So the SoC is the idea that you put many things on the same chip surface. You have a GPU there, you have all sorts of, maybe a modem, things like that on the same chip. And Intel definitely builds SoC chips. Very good answer. So we work with Intel as well, but Intel doesn't use the ARM architecture, obviously, for this. They use ARM for other things. Okay. Let me motivate a little bit. The use of TPMs in industry and the research community is growing. For example, operating systems built by Microsoft and Google use all sorts of features that rely on TPMs. Enterprises especially like these features quite a bit. Also, the research community has put forward many different ideas that rely on TPMs, whether sort of secure hypervisors or trusted sensors, not just our work, but other people's work, things that sort of leverage trusted. TPMs are basically a form of trusted hardware, and people have leveraged that to build all sorts of interesting things. Now, most smartphones and tablets, and I'm very cagey when I say most, I could say all of them. I'm not really aware of a popular smartphone or a popular tablet, do not have TPM chips in them. And the reason, there is nothing fundamental about that. You can put a TPM chip in a smartphone, so you could. There is absolutely nothing that stops you from doing that, but there are reasons in practice why people don't do that. TPM chips were not designed for the power constraints and the space constraints of smartphones. Smartphones, there is a lot of real estate is at a premium inside of your smartphone, and TPM chips typically are big. They don't have to be big. Somebody can invest a ton of money to actually make them smaller. It's nothing fundamental, but they're not sort of shipping in smartphones today. However, in recent years, commodity CPU vendors like Intel and ARM have started to offer commodity trusted computing extensions in their chips. For ARM, the set of trusted computing extension is called TrustZone. And for Intel, it's called Software Guard Extensions, or SGX. How many of you have heard of SGX? Or even fewer than ARM, okay, than TrustZone, okay. And the question here is, or what CPU manufacturers try to do is to try to say, okay, can people actually use these CPU extensions to build systems that are equivalent to those of TPM chips. And what I have there on the right is a picture of a TPM chip. Well, the problem is, that's great, but there is a big problem. And what I forgot to say, what these things here on the left, they are CPU extension, and what they offer is an isolated runtime from the rest of the system. So you have your own runtime, they're sort of isolated from everyone else. And that's useful. But you need many more things in practice. One of the things you need in practice is trusted storage. You need to be able to store your data somewhere when your computer, when your machine, whether it's a smartphone or a desktop PC, when it's off. When it's turned off, you have to store it somewhere. And that thing needs to be trusted, and I'm going to talk about that. You need a secure clock, you need a secure counter, you need a secure form of entropy to create keys and randomness and things like that. And all these omissions raise an important question. So sort of from a research standpoint, can we actually overcome these limitations to build something interesting in practice? And the answer is we could in this particular case by building a firmware, a TPM in software, but we have made some trade-offs, and I'm going to talk about that. So what we did was, and what the contributions of this part of the talk is, I'm going to tell you about the 3 approaches we use to overcome these limitations that platforms that extensions like TrustZone have. And many of these lessons are relevant to SGX. We did not build a firmware TPM for SGX in this particular work, but many of these sort of observations are similar to SGX. SGX is Intel, TrustZone is ARM. I'm going to tell you how the firmware TPM from a security standpoint is almost identical to the TPM chip in what it can offer, but not quite. And I'm going to talk to you, I'm going to give you a security analysis. And yeah, finally, the FTPM shipped on all the devices that Microsoft has with SoCs, like Microsoft Surfaces and Windows Phone. So if you buy a Microsoft Surface, chances are it has an FTPM inside of it. Not all Surfaces have firmware TPMs, because some Some of the surfaces are made by Intel, and in some of these SKUs, in some of these models, Intel puts actual TPM chips inside rather than a software-only implementation. Okay, so this is the outline of my talk. I want to talk a little bit about background, and I'm going to tell you about TPMs and trust zone first, and then I'm going to tell you about the FTPM. So let me just move on. Background on TPMs. So trusted platform modules. These are secure co-processors, and their role is to act as a hardware root of trust. TPMs provide a small set of primitives that can offer a high degree of security assurance. One of the things they offer that is very useful in practice is a machine identity. So these are not IP addresses, right? IP addresses can be spoofed. There's all sorts of bad things with IP addresses. This is a strong machine identity. And the way they offer that is by offering basically a private-public key pair that's binded to the TPM. And the TPM offers a very nice property, which is that the private portion of the key pair never leaves the chip. So you can have malware on the machine, you can have anything you want. The private key, the private part, the private portion is never going to leave the TPM chip. It's not going to be available for the hardware, for the malware to steal it. And this key can act as effectively as a global unique identity. TPMs can also offer undesired software rollbacks. They can offer isolated and secure storage of credentials on behalf of applications and users, and they can attest the identity of the software running on the machine. Okay. TPMs are old. The spec has been out for more than a decade, and although it's been out for more than a decade, we're kind of seeing now a resurgence of TPMs. What happened is in the past, TPMs have had sort of a mixed history. The initial perception when the TPM chip was released is that sort of the scenarios that everybody talked about was DRM and digital rights management, and there was this perceptions that TPMs are sort of an attempt of industry to actually take over the machines that owned by users. And over time, TPMs have sort of been able to overcome this mixed reputation. And they've put, Windows and Chrome OS actually have a whole bunch of features that rely on TPMs, and the research community as well, and I talked about it. Okay, I'm going to skip. I'm not going to talk about all these papers about they use TPMs in all sorts of interesting ways. So as I said, the TPM specification has been around for a long time, more than 10 years. I'm not going to go in detail on this slide. The point of this slide is, there are 2 points of this slide, is that there are many different versions of the TPM specification. The most popular version out there is TPM 1.2. Chances are that many of the TPM chips in these rooms actually run version 1.2. The current version is 2.0. And pretty much the first approximation, if you buy a machine today with a TPM chip inside it or a firmware TPM, it runs 2.0, not 1.2. What's new in 2.0? We have better cryptography. So for example, one of the things we have in all 2.0s I'm aware of is elliptic curve cryptography, not just RSA, and that's nice. The other nice thing is that with TPM 2.0, we have a reference implementation. And what that means is in 1.2, we had a spec, and the spec was done in English. And because it was ambiguous, so different implementations of the TPM done by different vendors are a little bit different. Now we have a reference implementation, so if you have a question about how the TPM is supposed to react or what is the output given the set of inputs, you just can run this reference implementation and find out. The other thing is that many of the TPM 2.0 chips you have today run this reference implementation inside of them. The firmware TPM runs that inside. By the way, what I want to say is that all research institutions, this includes universities and so on, can become members. There's a particular level of what's called the TCG, or Trusted Computing Group, and it's a free tier for researchers out there. And the moment you're a member, you have access to this reference implementation. It's an interesting sort of piece of code. It's really well engineered that builds a TPM. It's sort of interesting. You can think about that for doing your sort of future research if you're interested. And then it has a whole bunch of more bells and whistles, and I'm going to skip over it. Okay, so I told you about TPM. Now let me tell you about ARM Trust Zone. So Trust Zone is ARM's proposal to do trusted computing. And this is the picture that basically people show when they look at Trust Zone. And what you see here is that the software stack can switch between two states referred to as worlds. One is the normal world, which is on the left, and one is the secure world on the right. And you can think of these worlds as being strongly partitioned, and you can think of them as being sort of virtual processors backed by hardware support. A different way to think about it, although it's not very accurate, is like two virtual machines. You can think of them like that. It's not very accurate, though, and I'm going to skip over that. So let me now show you this picture of what happens when the ARM chip, the SoC, boots up. So the ARM hardware powers up. You turn on power. The processor then enters a mode called secure monitor, and this is a software mode. And in this mode, the software can actually provision the two worlds. So for example, it can allocate memory to the secure world only that is strongly isolated from the normal world. Okay, and this is very important. It's your legacy operating system does not even know about the existence of this other part of memory where you actually can run things, and that's very powerful for security. The CPU has two separate banks of registers for each of the two worlds, and there is one special register that determines whether the CPU runs in the normal world or in the secure world, and only the software running in this layer has access to that register. Okay. Then the secure world is booted. Okay, so the software here allocates some memory, and then it boots the secure world. And it's very important to point out that the secure world boots first. So all the code here now in the secure world has a chance to run and sort of initialize itself and so forth. So at this point, there is nothing third party on the platform that we've run. So that's safe. There is, chances are there is no malware. And at some point, the secure world says, I'm done, and then the normal world runs. And the normal world is, well, all your applications actually run, things like, your Android operating system or your Windows operating system or whatever. And then you switch back and forth between the two worlds. Okay. So to summarize, the properties of trust zone, we have an isolated runtime that boots first. We have what's called curtained memory. Curtained memory means memory that is curtained off from the normal world. So the normal world doesn't even know it exists. And the third thing that is very powerful for trust zone, this is one thing that HGX does not have. Trust zone offers the ability to map interrupts to the secure world. So what you can do right now, you can do really trusted. This is how we did trusted sensors. We do sensors and we map their drivers into the secure world, and we have a small piece of code that basically reads the sensors. So we can be assured that there is no third-party code running around trying to alter the sensor reading. Okay. You can also build trusted networks, or you can build, sort of your favorite form of trusted I/O. Okay, like I said, ARM Trust Zone suffers from several limitations. One is that the Trust Zone specification is silent on trusted storage. Okay, so where do we put the state when the platform is offline? And one idea is, well, we can encrypt the state and write it on the disk. Of course, encryption works really well. The question is, where do you keep the encryption keys? You can't put them on the disk, because then it makes no sense whatever you encrypt. If you have the keys on the disk, you're done. Second, there is no secure counter. And this is very important. Yes, we can encrypt the data. Encryption works really well, but encryption does not prevent against rollback attacks, where an attacker can take the encrypted blob, throw it away, and replace it with also an encrypted blob, but an older encrypted blob. It's older encrypted blob. It's a rollback attack. And for TPMs, rollback attacks are very dangerous, and not just for TPMs. Finally, there is no secure clock, there is no source of entropy present in the specification, and the FTPM needs all these hardware resources. And not just the FTPM, anything in security, if you want to do, you need these things. There is nothing esoteric about them. I would like to mention two more things before I move on. ARM Trust Zone does not have support for virtualization, and this makes life very, very hard. And I'm going to talk a little bit about that. And also, although all ARM SoCs you buy today, not all, but in all your smartphones, in many of your smartphones, you run an ARM chip. The ARM chip has Trust Zone inside of it, but access to the Trust Zone is often disabled. So it makes it hard to do research on Trust Zone, although nowadays it's actually much better than it used to be. You can buy Raspberry Pi platforms that give you access to Trust Zone and other platforms, so you can do sort of more interesting things. The reason why we got lucky is that because we work for Microsoft, we're able to interact directly with these companies and have them give us access to the Trust Zone. Okay, so this is the high-level architecture of what we built. One of the things before I tell you what this means is that these boxes are not at scale, so don't look at the size of these boxes to compare different things. We have the SoC hardware there. We have a trusted execution environment. You can think of it like a very small operating system. And then we have a dispatcher runtime, and at the top we have the firmware TPM, and we run other secure services. The FTPM is one secure service. Everything that's in the shade here, it's the TCB, the trusted computing base of our system. And on the left, we have the normal world like commodity operating system. And again, this picture is not to scale because the number of lines of code in the Linux and Windows OS is way, way bigger than everything else here, okay? Oh, the other thing I should say is that most hardware resources were mapped in the normal world and not into the secure world. Why do you think that is? It says on the slide, but why? Performance. So, good answer. So you can definitely build trusted hardware. In general, on the smartphones, we want all our hardware to be very fast. If it's done in the secure world, then it makes it harder to sort of have its readings go to the normal world. And there are more context switches back and forth, and that makes it slower. And we don't like that. Okay. I should talk about the thread model. Maybe yeah. So these are threads that are in scope, and what I have here on the left are 6 attacks that we're worried about. And there I'm having the firmware TPM and a TPM chip. And I'm talking about what's in scope and not what's out of scope. So I'm not talking about things that we defend against. So I'm going to use sort of funny notation for that. So malware clearly are in scope. We care about malware and we think about the firmware TPM and the TPM. The TPM chip clearly wants to defend against malware, and we're on the firmware TPM to do the same thing. The second attack are time-based side channel attacks. These attacks are gaining scope. The TPM goes to great length to make sure that the cryptography they use is constant time. Next one is cache-based side channel attacks, and again, they're in scope. We want the side channel attacks that use the cache to be ineffective, and the trust zone spec has provisions against that help you with with cache-based side channel attacks. One of the things I should mention, and I don't mean I mean this in a nice way. There are some papers nowadays that show how you can attack trust zone by mounting these cache-based side channel attacks. And you can definitely attack the trust zone that way. But if the code running the trust zone leverages the hardware properly, these attacks will not be effective. Now, more interesting, let me talk about the attacks that are harder to defend against. Denial of service. Denial of service means that your operating system wants to disable a TPM and not offer service to it. And there's nothing we can do about that. Again, the point here is that whatever data we protect with the TPM or the FTPM remains secure, but we cannot make forward progress, okay? So there's nothing, we're similar to the TPM that way. Power analysis-based side channel attacks are also out of scope, sort of having radio antennas that measure the electromagnetic emissions of your TPM chip or the firmware TPM. You can attack things that way, and TPMs were never really designed to stop this kind of sophistication of attacks. We don't defend against them. But the thing I should talk about is memory attacks that are very problematic. The firmware TPM stores all its state in memory, in actually the DRAM of the device. Whereas the TPM chip, the state is actually in the chip itself, it's not in the DRAM of the device. So now you can actually leverage well-known DRAM attacks like cold boot attacks to attack the FTPM. And we worried about this. In this talk, we did not prevent these attacks. You can mount cold boot attacks to attack the FTPM chip. The TPM chips are resilient to cold boot attacks because they don't store its state in memory. However, there is a different kind of attacks on TPM chips where people were able to sort of scrape the surface and mount and try to read through electron microscopes the key in the TPM chip, okay? However, the second part of my talk, if I get to it, actually mentions some ideas around how to prevent memory attacks. Okay. So now let me tell you how we sort of overcome these things. One of the things we sort of an obvious way, we need these resources for the FTPM, and we don't have them. And And a naive question is, well, you don't have them. Why don't you go to the SoC vendors, to the Intel and NVIDIAs of the world, and say your SoC should have these resources? And there are two reasons why that's hard. One reason is economical. These vendors actually care about their what's called the bill of materials being low, cost being low. What that means is that they care about any hardware resource they put on these platforms to be very, very cheap. Any bump in price, even by 5 or 10 cents, is a huge cost for them. The second reason is much more fundamental, even if you're able to overcome the first reason. These are core chips. They're hot. We really don't know from sort of the engineering level, from material science, how to put flash for storage on a hot surface like that of an SoC. We don't know how to do that. So it's sort of physically difficult. However, we've made a couple of helpful observations. First, ARM comes with a huge ecosystem of vendors out there. There are many vendors that all try to differentiate among themselves by offering special hardware. And it turns out that many ARM SoCs offer this storage controller that has extensions for trusted storage. And I'll tell you what it is. It's called an eMMC, and it's present on many of the ARM SoCs out there. Second, there are also secure fuses. Secure fuses think of them as register where you write them once and you cannot rewrite them overall after that. So you can read them as many times as you want and you write them once. And what's a secure fuse, and I'm going to jump ahead a little bit, what's nice about that is that we can have a secure fuse that is only readable from the trust zone, from the secure world. So we can write something in it and then we can read from it again and again and again. What do you think we wrote in some of these secure fuses? Yeah. What? The keys. Excellent. You got it, but no. In the sense that you're right. We didn't write the keys there. And I'll tell you why we didn't write the keys. This is great. We didn't write the keys because we want to be able to change the keys. And TPMs actually rotate keys. So when TPMs have these provisions called TPM ownership, and they're meant for, I just want to sort of re-own the chip. You can think of it, I'm going to give my machine to someone else. And then you rotate the keys. So what we wrote was entropy. And now sort of a random seed. Now if I have, not entropy, a random seed. Now I have a random seed and I can have a counter. And I'll tell you how we get a secure counter. I can generate my keys and I can rotate them by incrementing the counter. Okay? Very nice. Good. Okay, so let me explain one slide on eMMC. eMMC has these provisions. You can actually take one partition and call it a replay protected memory block, an RPMB partition. RPMB stands for replay protected memory block. And it has a number of useful primitives. It has this sort of secure fuse on the storage controller itself. It's not a secure fuse. It's actually a one-time programmable key. So what you do is you have this entropy in the secure fuse in the trust zone. You boot up, you create your encryption keys, and then at device provisioning time, before the device was sold, we write the key to the storage controller. So, and that key is written once, and you cannot overwrite it. You cannot do anything about it. It's written once, you're done. So what it means that by the time a user buys the device, we now have a shared key between the trust zone and the eMMC. And then this key does not get rotated, by the way. This key is only used for communication purposes. The TPM itself has keys, and we rotate those. It also has support for authenticated reads and writes, and uses internal counters, and it has nonces for freshness. Okay, so now we have an eMMC, so we have trusted storage. Because we have this eMMC, we can also build secure counters that way. So we can have a counter that we can guarantee it only moves forward and not backwards. And this is done through the authenticated writes and reads that the eMMC has. So we got those two. We actually got lucky, and it turns out that you can put entropy in the SoC. So we actually asked the OEM vendors. And then we build a secure clock in a different way by using a timer. It's not a perfect clock. It has the ability to move forward. But you don't know, it can move forward faster than the wall clock. We cannot guarantee that it doesn't move faster than it can. but what we can do is we can guarantee that you cannot roll it back. So we kind of fudge here the clock, and we disable the portion of the TPM specification from our FTPM that rely on the fact that the clock cannot move forward faster, because we know it can move faster. Because it can move faster, we said, okay, this part of the TPM we cannot offer it, so we disabled it. Okay, I'm not going to talk about that. I talked to you about how we provision trusted hardware. The other thing we did was we made some design compromises, and I want to tell you about that next. So everything this part of the work is we had to be very careful because we didn't want to make the FTPM insecure in some way. So everything has to be done with great care. Okay. So here's a problem we have. One of the problems is that is long-running commands. So let me start this problem by describing the design requirements. The code running in the secure world must be minimal because so for example, the trusted execution environment, that operating system we build in the trust zone, does not have preemptive scheduling because it requires quite a bit of code. So we cannot really switch back and forth very quickly between the two worlds. We also don't have support for virtualization and things like that. So what this means is that the firmware TPM commands cannot be long-lived. The reason why they cannot be long-lived is because whenever the FTPM executes, your commodity operating system, Windows in this case, freezes. And operating systems really don't like to freeze for a long time because they like to be able to service their interrupts. And while the OS is frozen, the interrupts queue up and you start losing interrupts. And that's bad. For example, we actually did this experiment where we froze Windows a little bit for a long time, and things don't work very well. So for example, listening to an MP3 to music doesn't work very well because you want Windows to sort of handle those interrupts and give you the proper sound. So by not being careful here, we were going to engineer a product that whenever you would actually run an FTPM command, your music will sound distorted. So that sounds stupid, okay? So we didn't do that. So how do we solve this problem? Another thing I wanted to say is that some of these TPM commands are very long-lived. Creating keys, RSA keys, takes a huge amount of time. And the reason why that is because the way creating RSA keys, you try to find prime numbers, and you just flip some coins and you try to find some big numbers and you test for primality. You test, is this number a prime? And if it's not, you throw it out and you start again. And sometimes you can get unlucky and you can try a lot of numbers until you find a prime number. So on some of our devices, it takes about 10 seconds to create prime numbers, to create RSA keys. So freezing Windows and Linux for 10 seconds without servicing, it's a terrible idea. Okay. So what we did was a very sort of old trick here called cooperative checkpointing. This is a trick from the operating system literature. The idea is, when you have the normal world here on the left issuing a TPM command, the secure world at some point says, well, I've been running for a long time, so rather than finishing the command, I'm just going to yield back. I'm going to checkpoint the command and send it back to the normal world. And it's the job of the normal world to call me back and resume it. Okay, so what this guarantees is that the amount of time here on the right between while the OS is frozen is short, and we can control how short it is. The normal world can also resume the TPM command, or it can cancel the TPM command. It can say, forget about it. I don't want you to continue later on. So it can because the two worlds are cooperative, you can actually jump back and forth. The third thing we did was we changed the semantics of some of the TPM commands, and I'm going to show you a very nice example of that. So let me tell you about TPM unseal. TPM unseal is a TPM command where an authorization is shown to the TPM in order for the TPM to decrypt an encrypted blob. So you can think of this authorization of being a PIN number. So when you boot, for example, with BitLocker, when you boot your laptop, you have to enter a PIN number. That PIN number is authorization that the software uses to go to the TPM chip and ask for the TPM chip for some keys to be able to decrypt your operating system. Okay? And the TPM uses a mechanism called anti-hammering, whose goal is to stop an attacker attempting to guess PIN numbers too many times. Obviously, PIN numbers are short, they're not very long, and you can mount brute force attack where you can guess it. So the idea here is to sort of stop an attacker from doing that. And let me show you this diagram and explain it. So this is how the TPM works. If an attacker guesses the PIN number incorrectly the first time, the TPM increments a counter and persist the counter to trusted storage on the TPM chip itself. So it's, increment the number of failed attempts. You guess a pin number a second time, again, we increment it a third time. At some point, the TPM enters what's called lockout, which means I'm not going to be able to, even if you give me the correct pin number, I'm not going to be able to, I'm not going to decrypt anything for you. I'm not going to even try to do anything because you've actually exhausted the number of tries you have. And this lockout lasts for a long period of time in the order of hours. And after a couple of hours, you can actually start your, entering your pin number again. And this makes sense from a security standpoint, right? Okay, what's the problem with the FTPM? The problem what's called these dark periods. A dark period is a period of time where we don't have access to storage. And the danger during this dark period is that a TPM unseal command are not safe. You cannot record that counter that you attempted to guess the pin number securely. An example of a dark period occurs during the boot cycle of all devices. At the moment that your firmware, and firmware here, I don't mean necessarily just the secure world, but there is firmware running in the normal world as well. You can think of it like the UEFI or like a BIOS. You can think of it that way. Between the BIOS, at some point, the UEFI stopped executing the BIOS of the machine, and it sort of relinquishes all the drivers from the storage, and it waits for the operating system to start booting up. During that period, we don't have access, we don't have drivers for the storage. And there's nothing fundamental about that. You can definitely imagine a system where you have some sort of handoff between the BIOS and the OS done better. But there are many reasons in practice why that not is. The biggest reasons being the fact that these are different companies running. The firmware running UEFI is not owned by Microsoft. It's owned by, for example, like Qualcomm. And Qualcomm has all sorts of secrets that run in their firmware, and they really don't like companies, including Microsoft, to look at their firmware. So they just say, look, we initialize the platform, now it's your job to go boot the OS. So we want during that period of time to, for example, run BitLocker. So running BitLocker requires us to actually have access to this storage to be able to count properly whenever an attacker tries to guess the pin number. This is a huge problem in practice. So let me illustrate that. This is the attack. We have a TPM or the FTPM, we don't have storage. You guess the pin number. So you enter the dark period here. You guess the pin number. We cannot store the counter. You guess it 3 times, and then you can reboot the machine and keep guessing. And then we can never stop you because we don't know how many times you've actually, we can record the counter in memory, but if you reboot the machine, that counter is gone because the memory is volatile. So how do we solve this problem? Well, we modify the semantics of the TPM, the way the TPM 2.0 interprets that counter. And what we did, we introduced this idea called the dirty bit. Before entering the dark period, we write this bit to storage. And when the machine exits the dark period, the dirty bit is cleared. Okay, so before we enter the dark period, we write something to the trusted storage because we have drivers. And when we exit, we cleared up that bit. Well, what happens if you reboot? Well, when you reboot, actually, the OS, the machine boots up again, and it sees the bit being dirty in memory, and it cannot distinguish between 2 cases. Either the machine is under attack, an attacker tries to maliciously attack the machine, or there is an unlucky user who just happened to reboot during that dark period. And we cannot distinguish between the two. And we take the conservative solution. We say, oh, the machine is under attack, and the TPM automatically enters lockout, no matter what. Okay, so that way we're safe. So just to illustrate the dirty bit in action, here, before we enter the dark period, we write these dirty bits. We don't have storage anymore, so the attacker keeps guessing the pin number. The attacker reboots, we enter lockout because we know that the bit is dirty. Okay? So you have to exit this dark period properly to clear the bit. Okay. Let me talk about performance. It's actually very cool. These are 7 devices we use in our performance evaluation, at least for this paper. We use 4 firmware TPM devices running on commodity ARM SoCs. These are commodity phones that maybe some of you own. And at the bottom here, at least 3 what's called discrete TPM. Discrete TPM means TPM chips. These are the old TPM chips. And we instrumented and measured TPM commands. And I'm not going to show you everything. I want to show you one graph, which is actually very cool. On the x-axis here, we have the 7 devices. The first 4 are firmware TPMs. The last 3 are discrete TPMs. And on the y-axis, we have how long encryption and decryption took on these devices with the RSA-2048 in milliseconds. And decryption takes longer than encryption most of the time. But what I want to point out here that's kind of very cool, the firmware TPMs are much, much faster than the Decrypt counterparts. Why do you think that is?
They run on much more powerful CPUs.
Exactly. They run on ARM SoCs, right? So the TPM device, the TPM chips are these chips that cost about, depending on who you ask, between 10 cents to 50 cents. They have microcontrollers inside of them that are very, very wimpy. The FTPM runs on the ARM core. So we have a huge A57 running at our disposal, and we run encryption much, much faster. So there's nothing smarter about the FTPM. It's just that we have better hardware under us. So what's interesting right now is that in general, applications never considered running encryption and decryption through the TPMs because TPM chips were very slow. If you run an application, you don't want to wait for the TPM to start decrypting your data. That's kind of silly. The way you would do this, you would ask the TPM to decrypt a symmetric key, and then you use the chip to actually decrypt things using the symmetric key. Now you can run the encryption and decryption of the TPM because it's very fast. It's as fast as you can probably do it. So it's kind of nicer that way. So you're not in the business of keeping symmetric keys in the normal world, in the regular operating system, which is probably a bad idea. That's nice. So I told you about the FTPM. I told you how we were able to overcome the limitations. The next slide I have, and I don't know if this is interesting or not. I can talk a little bit about limitations on SGX. And the nice thing about SGX now at the end, at this point, is that you have some background on trust zone, and you can now compare it with SGX. But I don't know if this is interesting. So I can skip ahead, or I can talk about this, and it's your job to tell me what I should do while I'm having a chartreuse. SGX? Yeah? Okay. So let me talk about SGX. So I have 4 bullets here. Not everything about SGX is bad, some is better. So I'm comparing SGX to trust zone. I talked about how we don't have trusted storage, secure counters, and clock on ARM trust zone. You don't have those on SGX. And again, you don't have them because these are extensions, CPU extensions. They're fundamental. Nobody's going to put flash storage on their SoC, or nobody can. I shouldn't talk about that. I'm not a material scientist, but I understand it's a very hard physics problem, okay, to do that because that surface is hot. So we don't have those, so you need those as well. The other kind of problem is that SGX is an Intel technology, and you lack this ecosystem unlike ARM, right? So if with ARM, you can go to company A and say, hey, company B offers me this eMMC, and I can do an FTPM that way. And then company A says, oh, maybe, now they have an incentive to sort of compete with company B. SGX is an Intel technology. You're at the mercy of Intel. Whatever they put in their thing, it's there. If it's not, it's not. They control the whole ecosystem. So Intel can put eMMC controllers on their devices, but you're at their mercy to do that. The third thing that's very nice is that SGX encrypts memory. And this is huge. It's a huge advantage over trust zone. Trust zone does not encrypt memory. Okay? And we don't need to worry about memory attacks with SGX anymore. SGX is actually very powerful precisely because of that. And finally, so that's a good thing about SGX. A less good thing about it is that SGX can only protect code that runs what's called ring 3 for Intel, so the application layer. So you cannot actually have secure interrupts. It's very difficult to build trusted hardware that way because your interrupts go to your operating system. So it's the job of the operating system to service interrupts, to service all your OS needs for the code running in the SGX. And because of that, I believe as a researcher that there are huge side channel attacks possible because if you have this malicious operating system under you that manages your resources. And some of these attacks have been shown already, and I think the SGX engineers are aware about these side channel attacks that are possible now. So this is a huge open door. Okay, I have 5 more minutes. Great. So let me speak for 2 more minutes. So I just want to give you a flavor of what we've done here. This is a research project. So This is an interesting paper. It appeared at ASP+ last year. What's interesting was this paper talks about how to protect memory, how to build basically encrypted memory in ARM. You read the paper, and it's kind of like we read this as a research paper. The motivation for this work was from the FTPM. The FTPM has all this state in memory, and we were worried about it. So we started looking at what can be done. And we came up with a couple of interesting tricks, and I want to talk a little bit about them. These tricks have not been shipped, though. So the FTPM today is subject to memory attacks. And these slides are all about motivation, and I'm going to skip over them because I gave you the motivation. So what this system tries to do is it basically tries to make sure that any sensitive data you might want to have can only be decrypted when the data is on the SoC, but not in DRAM. So we can guarantee that the moment data leaves the SoC, the perimeter of the SoC, data is encrypted, okay? And the reason for that is because attacking memory is much more inexpensive, it's much easier than attacking the SoC. You can definitely attack the SoC, but that's hard, and if you attack the SoC and you're successful, more power to you. We don't stop that. The other nice benefit about Sentry is that it works with today's ARM-based mobile devices. So there's nothing sort of tricky about it. So let me show you what we've done. Before I show you this animation, so I said that Sentry can offer encrypted memory. Making all the memory encrypted and encrypting at all times is very costly. It's very performance costly. It's very expensive. So we made this very simple observation that actually, in retrospect, it's obvious, but it took us a while to realize this. When your device, so we know that you can lock a device, right? You can pin unlock and pin lock. You use a pin number. If the device is unlocked and you lose your device, we don't encrypt the memory anymore. Why? Because if an attacker has access to your device and the device is not locked, the attacker can simply turn it on and read the data. So we're not going to stop that. But what we want to do is want to make sure that when the device is locked, memory is encrypted. And I'm sure many of you use PIN numbers for your devices. Enterprises in general mandate their employees to use PIN numbers. If this is my personal phone, I bought this phone, but Microsoft, as part of my of Microsoft employee policy, if I want to be able to use this phone to access company data, like for example my work email, I have to have a PIN number. So I have a PIN number, and the moment you turn off the device, you have to enter a PIN number again. So here's the idea. So when the device is unlocked, so this is how Sentry works. When the device goes from an unlocked state to a locked state, we encrypt. We don't encrypt, by the way, all the data. We only encrypt the applications that are sensitive. So our idea is that you go to your settings menu and you say these applications are sensitive and these are not. So for example, and the reason we do that is for performance reasons. So for example, if you listen to music, we don't think that's a sensitive application. You really probably don't worry about an attacker stealing your phone and looking at what music you listen to. But if you're using a wallet application or some health application, we worry about that, or email. And when the device moves back from this state to this other state, we decrypt on demand lazily. But when the device is locked, the device continues to compute, right? I continue to receive email when the device is locked. So we want to be able to run these sensitive applications while still on SoC. And I'm going to show you, I'm going to just jump to, I'm going to skip about all possible attacks you can mount on memory and the threat model. And I'm going to just jump to this animation, and I'm going to stop. So this is what happens with Sentry. On the right here, you have DRAM. The yellow pages are unencrypted pages. And the red pages are encrypted pages. And the blue sort of outline there means that's a sensitive app. So the reason why those two pages at the bottom are not encrypted, because they're not sensitive, we don't care about them. Okay, so we keep data in DRAM at the granularity of pages. On the left here, we have SoC, and we have limited amount of SoC memory on the SOC memory. This can be IRAM, or we can actually have a very nice trick where we can use the L2 cache to store things on the SOC, and I'm not going to talk about that. So and when the device is locked, as you can see, the sensitive application is actually encrypted. Well, what happens if one of these sensitive applications wants to run? Well, it's encrypted, the memory page. So what we do is something very, very simple. We first take the page, that encrypted page, and we copy it into the SOC memory. We then decrypt it in place, which is actually sounds simple, but it's actually was a little bit of engineering effort. You cannot run a willy-nilly decryption algorithm here, because if you run a decryption algorithm in your operating system, that decryption algorithm is going to, it's the program, so it's going to start using the stack and things like that, and it's going to start leaking things to the DRAM. So we wrote something by hand to make sure that the encryption, everything is done using registered on the SOC. So we decrypt in place, and we just take the page table and we point to that page. And now, and then we let the application run. So now the application can run, it has access to each page, while the page in memory is actually remains encrypted. And when the device is locked, we basically, sorry, this is an animation showing that we sort of point the page table there. And when the device is locked, and when the device is unlocked, then we don't bother to encrypt the page anymore, because I just told you we don't do that anymore. And there are all sorts of problems here. I didn't talk about it. The amount of memory you have here is very, very small, so you have to be very aggressive, and what you keep in memory and so on. I'm going to stop now. So this is the trick we used. It's actually quite a nice trick, and I think there is sort of an interesting direction here to pursue and sort of make this more interesting. I'm out of time. I'm happy to take questions. I can have more chartreuse too. I hope you got something out of this. Any questions about anything big or small? Come on. Yes, you. Yes, absolutely. So let me try to rephrase the question or repeat the question, and you tell me if I got. So the question is, well, you do I/O, you need hardware, and where are the drivers for the hardware? Where do they live? Do they live in the secure world or in the normal world? And if they live in the secure world, aren't they an attack vector? So let me start. Anything that's in the secure world is an attack vector. There is very little. So like I said, all the drivers. The majority of the drivers on the platforms are all mapped to the normal world, okay? So the only driver that we have for the secure world, it's for the trusted storage for the RPMB. And the way we do that is actually very kind of tricky. We don't run a driver in the secure world. What we do is we use kind of like power virtualization. So we sort of do the right thing and we push it over to the normal world, to Windows, and we have a driver in Windows whose job, everything is encrypted at this point, the job is to write. So it allows us to format a message to the storage controller and encrypt it in such a way that's safe for Windows to actually, Windows' job is just to copy it back and forth. Can Windows attack it? Yes, it can, but it has two options. Either break the cryptography, which is very hard. I mean, if you break the cryptography, you're done. Or it can drop it. It can say, screw you, I'm not going to service this packet, this message. And like I said, that's a denial of service. And yes, we cannot prevent against that, but we remain secure. There was another question in the back. Yes? So the question was, if you're making it a too secure device, are we afraid in hampering legal operation? Yeah. So in general, I mean, I'm not speaking. This question is sort of has many layers, and I'm not again speaking on behalf of Microsoft. There are many. People at Microsoft that have much deeper expertise in the legal question. But what I can tell you is this: so right from a legal standpoint, when you get subpoenaed, and in the United States, as far as I understand, you can get either subpoenaed by any judge to first approximation or under the Patriot Act, and the difference there is only the fact that in one case you can disclose that the act of subpoena, whereas in the other case, actually you're not allowed to. the company is obliged to actually do the best it can, not to an unreasonable burden, to comply with the law. I'm a researcher. Our goal was to, for us, our goal was how can we build an FTPM that actually is as close to a TPM as possible. If you think that there's something in the TPM design that can be subverted in some way, we are subverted as well. I don't really, when I worked, one more thing I should say, actually, and this will alleviate. When I work on these things, so maybe I was not a US citizen at the time. If you're not a US citizen, you cannot actually interact with, or you know, with some of the agencies that might be interesting here. I become one since, so maybe if I come back next year, I have more interesting things to tell you. But I do know that there are actually meetings between software companies and institutions like NSA, but they are only subject to legal US. So I don't know. I mean, as a researcher, I'm not. Microsoft is, you know, ships TPMs. They make a ton of money from the features Windows has that rely on TPMs. They're happy to invest, and in general, Microsoft actually has, and you know, I genuinely think this is true. It has more interest. It has a deep interest in security because of its history. So they've always invested more in security, at least in the last decade, than other companies. So it's sort of, you can see these projects. I don't know if I really answered your question, but
thanks, Stefan.
okay, thank you.
If we're out of time, you can always ask Stefan another question.
I'm all day here today, so I'm not going anywhere. Yeah.
So please give a big hand to Stefan.
Thank you.